Okay, good evening. In this video, we are going to be looking at magnetic field. Actually, especially the calculation aspect, that has to do with everything magnetic field, electromagnetic, and so on. Okay, so let's get started. Now, by definition, magnetic field is a region of space where magnetic force is experienced. It is also a region surrounding a moving charge. Okay, so when that also means that when a charge is moving, it generates magnetic field. Okay, so magnetic force is experienced when two or more magnetic fields interact. A magnetic force is experienced if two charges is moving relative to each other. Okay, so when a magnetic field interacts with another magnetic field, a force is experienced. Now, this leads us to the next thing here, which is magnetic force on a moving charge in a field. Okay, so a charge Q moving in a magnetic field B experiences a force which is equal to F equal to Q V B sine theta. Okay, F equal to Q V B sine theta. Now, what that means is that the force experienced at that charge depends on the magnitude of the charge, which is Q, the velocity of the charge, which is V, and the magnetic field with which the charge is interacting with. Then sine theta, which is the angle, the charge makes with the field. Okay, so any object that moves in a magnetic field, any charged object that moves in a magnetic field will experience a force which is equal to QVB sine theta. Okay, let's see questions here. This says a proton enters a magnetic field of flux density 1.5 Tesla with a velocity of 2 × 10⁻⁷ meter per second at an angle of 30 degrees with the field. Calculate the force on the proton. Okay, we are also asked to calculate for theta equal to 90 degrees. Okay, so based on what we have there in the solution, you can see that F is equal to Q VB sine theta. Okay, and the charge, so this will be equal to the Q here is charge of a proton. Now, I want to say this, that the charge of a proton is actually constant. Charge of a proton is constant, okay? So, that means it is 1.6 × 10⁻⁻19. So, that means this force now will be 1.6 multiplied by 10⁻⁻19. That's my force here, okay? Now, multiply by the velocity. The velocity given here is 2 × 10⁻⁷. That's the velocity of the charge. Okay, now at an angle of 30 degrees. Okay, let's see B. What is B? The magnetic flux is density is 1.5 Tesla, so multiply by 1.5. Okay, then sine theta, which is sine 30 degrees. Okay, so if I calculate this, that's 1.6. I have a calculator by my side here, so I'm trying to get that quickly. 2 × 10⁻⁷ multiplied by 1.5, then sine 30. Okay, so that is giving us a value of 2.4 × 10⁻⁻12 newtons. Okay, so this is what we are getting, 2.4 × 10⁻⁻12 newtons. Okay, so let's see. Sorry, we are not done with that question. There is the second question there that says that we should calculate when the theta is 90 degrees. Now I want to say this: when theta is 90 degrees, it means that your force is just simply going to be QVB. Now, why is it just QVB? Because sine theta, okay, let me put it this way, sine 90 is 1, you can try with your calculator, so you have just QVB. Now, if we substitute value, your Q, like I said, is constant, 1.6 times 10 to the power minus 19. Now, multiply by V, which is the velocity, 2 times 10 to the power 7, okay? Now, multiply by B, which is the flux density, which is 1.5 Tesla. And if we do that, we are going to, let's see what we get there. We are going to get 4.8 times 10 to the power minus 12, so equal to 4.8 times 10 to the power minus 12 newtons. Okay, so this is what is obtainable whenever you see a question where a charge, a proton, electron have the same charge, which is 1.6 times 10 to the power minus 19, or any charge at all moving in an electric field. It must experience a force, and that force is equal to the magnitude of the charge, which is Q, the velocity of the charge, which is V, the flux density, which is also magnetic field strength or field intensity, which is B, then the angle. Okay, so that leads us to the next thing. This is the part of a charged particle in a magnetic field. Okay, so a charge moving in a magnetic field describes a circular path. That's important for you to know. Whenever there is a charge moving in a magnetic field, let me pick another color to write it. Now let's assume that we have a magnetic field around this way, okay, and you pick a charge. Now, and a charge is being fired into the magnetic field. Immediately, once the charge gets into the magnetic field, it will experience a force which is perpendicular to the field, and that force causes it to rotate in a circular path, just like this. It rotates in a circular path. Okay, so with that we can say that there is a balance between the force, the magnetic force, and the centripetal force, because centripetal force is the force that makes an object moves in a circular path. So let's read. It says a charge moving in a magnetic field describes a circular path. Since the force is perpendicular to V and B, hence there is a balance between the centripetal force and the magnetic force. Okay, there is a balance between the centripetal force and the magnetic force. So you can see here where we say QVB, okay, QVB is equal to mv squared. QVB is the magnetic force. Remember, it describes, because the direction is perpendicular. And who gave that rule? That's according to Fleming's left-hand rule. Okay, so QVB is equal to mv squared over r. mv squared over r is called centripetal force. QVB is the magnetic force. There is a balance. So with that, we can see that r is equal to mv. By the time we cancel, if you say you have QVB, which is equal to mv squared over r. Okay. Now, as we equate QVB to be equal to mv squared over r. Okay, if we divide both sides by v cancels v. Okay, so we are going to have QB equal to mv all over r. So that means that my r now will be equal to mv all over QB. That's exactly how we have this formula. So when you are asked to find the radius of oscillation, r is simply mv all over QB. Okay, now which is exactly what we have. Another way the formula can be written is that omega is equal to QB all over m. And then why do we have that? If you say r is equal to mv over QB, under circular motion, if you remember very well, v is supposed to be equal to omega r. Okay, so if we substitute that there, r will be equal to m omega r all over QB. So if I make omega solid of formula now, omega now will be RQB all over MR, which by the time we cancel out R, you see that omega is equal to QB over M. So if we are asked to find the angular velocity, it is QB over M. Good. So let's see questions here. This says, what might be the mass of a positive ion with a single charge, okay, which is moving at 10 raised to the power 7 meters per second and is bent into a circle of radius 1.5 millimeter by a magnetic field of 0.134 Tesla. Okay, here we are asked to find the mass. Now, of course, that's the formula we use, R equal to mv over qb. Now, if we should substitute the values, we have R is 1.55 meters, or rather still, let's make the mass subject of formula. So making M subject of formula will mean R QB all over V. Okay, so that will now be equal to the R, which is the radius, is 1.55. The Q, which is charge, is not given, so we'll just leave it as Q. Your B is 0.134. Okay, now divided by your V, which is the velocity, is 10 raised to the power 7. Now, because Q is not given, there is nothing we can do about that. We're going to leave our answer to be in terms of Q. So while I calculate this with the calculator close to me, we have 1.55 multiplied by 0.134, then divided by 10 raised to the power 7. I'm getting 2.077 times 10 raised to the power minus 1, 2, 3, 4, 5, 6, 7, 8 minus 8 Q. Okay, minus 8 Q kilogram. Now I left my answer in terms of Q. Why? Because the charge in this question is not given. Okay, so this is another question. It says an electron moving with a kinetic energy 6 times 10 to the power minus 16 enters a field of magnetic flux 4 times 10 to the power minus 3 Tesla at right angles to its motion, of course. Calculate the radius of this part. Now, if you notice, we already know the radius of the part is mv, mass times velocity all over qb. But in the question, we are given mv squared. Okay, we are given kinetic energy, which is half mv squared. Now, the only thing that we can find there is velocity. Since we know that kinetic energy is half mv squared, the kinetic energy is 6 times 10 raised to the power minus 16 joules, okay, which is equal to half times m is the mass. If you look at the question, we are talking about electrons, so mass of electron is constant, which is 9.1 times 10 to the power minus 31. Okay, this is what we should know. Then multiply by v squared. We are looking for v squared. So v squared now, if we cross multiply, is going to be 2 times 6 times 10 to the power minus 16 divided by 9.1 times 10 to the power minus 31. So I'm on my calculator here. I have 2 times 6 times 10 to the power minus 16. Okay, now divided by 9.1 times 10 to the power minus 31. Okay, that gives us an answer. That is 1.3 32 times 10 to power, I think that's 15. 4. Yes, 10 to power 15. So that's the value for v squared, but we are looking for v, so we'll find the square root of that value. So the square root of that value, excuse me please. So let's quickly look for the square root of 1.32 times 10 to the power 15. And that will give us 3.63 times 10 to the power 7. 3.63 times 10 to the power 7 meter per second. Okay, so that's the velocity. Now that we know the velocity, it's now easy for us to find the radius of the part. Okay, so let me rub this off quickly. Now, the radius of the part now will be equal to mv over qb as we have in this formula here. What is m? M is mass of electron, which is 9.1 times 10 to the power minus 31. Now multiply by v. V is the velocity of the electron, which is what we just got now, to be 3.63 multiplied by 10 raised to power times 10 to the power 7. Now divided by q is charge of electron, that's a constant value, which is 1.6 times 10 to the power minus 19. Then multiply by b. B is the flux density, which is 4 times 10 to the power minus 3. Okay, so I'm with my calculator here trying to achieve that. So we have 9.1 times 10 to the power minus 31 multiplied by 3.63 times 10 to the power 7. Okay, the denominator there we have 1.6 times 10 to the power minus 19 multiplied by 4 times 10 to the power minus 3. And that will give us 0.052, so approximately 0.052 meters. So that's the answer to that question. I guess this is quite interesting, easy. Okay, so that leads us to the force on a current carrying conductor in a magnetic field. And what we saw earlier was the force on a charge moving in a magnetic field, but here we are looking at the force on a current carrying conductor in a magnetic field. So to explain that, if we have a conductor, let's say we have a conductor this way, and we have it placed in between two magnets, okay, and so let's say maybe this is north and south pole. Current is flowing along the conductor. Now something happens, because as current moves, it generates magnetic field. It will interact with the magnetic field of the magnet. The magnetic field generated by the current will interact with the magnetic field generated by a magnet, and that will give rise to a force. And we are saying that the force that will be experienced is dependent on three things. It's dependent on the current, I, the current flowing through the conductor, L, the length of the conductor, and B, the magnetic field, and of course also sin theta. That means the angle with which the conductor makes with the magnetic field. Okay, that is important for us to note. Now we see a question here. It says determine the magnitude and direction of the force on a horizontal conductor 5 cm long and carrying 30 amperes of current from south to north, if placed in air in a horizontal magnetic field of flux density 0.8 Tesla, directed from east to west. Okay, now in this very question, first of all, we can see that the length of the conductor is 5 cm. 5 cm means 0.05 meters. And then the current I is equal to 30 amperes. That's the current flowing through the conductor. Notice that the current is flowing from south to north. Now, if placed in air in a horizontal magnetic field of flux density, so your B is equal to 0.8 Tesla. And notice that it is directed, the field is directed east to west. You know why? It means that theta is 90 degrees. if the current is directed south to north, this is north, south to north, and while the magnetic field directed east to west, so it means that the angle between the field and the is 90 degrees, so theta is 90 degrees. So this is the formula we are going to use, F equal to ILB sin theta. So that will be equal to the I, which is the current, is 30. From what we see here, your L is 0.05 multiplied by B 0.8. And of course, we have sine 90 multiplied by sine 90, okay, which is the direction. So if we multiply that, 30 times 0.05 times 0.8, it's going to give us 1.2. So the force experienced here will be equal to 1.2 newtons. Okay. Now, this is another question based on this. A wire 15 centimeter long is at right angles to a uniform field of magnetic flux density 0.4 Tesla. What is the force on the wire when it carries a current of 6 amperes? Okay. Then actually that question is what is the maximum force. So please, the A is what is the maximum force. Then B says what is the force if the wire makes an angle of 30 degrees with the field. Now the force is maximum when you say F is equal to ILB sin theta. Now at maximum force, your theta must be 90 degrees. Your theta is 90 degrees. So, and sine 90 is 1. So we are left with F equal to ILB. So from the question, the current in the question here is 6 amperes. The length of the wire is 15 centimeter, which is 0.15 meters. B, which is the flux density, is 0.4. So we have 6 times 0.15 times 0.4. That will give us 0.36. So this will be 0.36 newtons. So the first A is 0.36 newtons. Now for the B part, it says what if is the force if the wire makes an angle of 30 degrees. In that case now, it is we are using this formula ILB sin theta. We already know what ILB is, which is 0.36. But this time around, 0.36, this time around we are multiplying it with sin theta. That means sine 30 degrees. And that will give us 0.18 newtons. Okay, so this is how it works. Okay, so another we are looking at is force on a current carrying loop placed in a magnetic field. Force on a current carrying loop placed in a magnetic field. Now, if it is a loop, just like the diagram we have here, look at this diagram. There is a loop, a loop drawn this way. This is the loop here, and it has to rotate. Let's say when it is placed in a magnetic field. Remember, this loop is carrying current. So if you place it in between a magnet, north and south pole, guess what? It will experience a force. That force it experiences causes it to rotate. The force it experiences causes it to rotate. Now, this is the principle, just to add, this is the principle that is used in creating things like galvanometer, moving coil galvanometer, things like electric motor, things like even ammeter, voltmeter, those things that are used to measure currents. You'll notice that when you plug them to current, they move, they deflect, they read. That reading, that deflection is because there is now an interaction between current and the magnet inside the device. Okay? Now, the force on the current carrying loop, because it is rotating, the force in a rotating object is called torque. Okay, that's what we have here, that the rotating force of a loop is called torque. And what is torque? I use this to remember very well, Barney sin theta. B is, of course, the magnetic field. A, there is the, A here is the area of the loop. N is the number of turns the loop might have turns. I here is the current. Then, of course, sin theta is the angle it makes with the loop. Okay, so This torque can also be written as mb sine theta. Of course, what does it mean? It means that m here stands for magnetic moment. It means that m here will be equal to BAN, and BAN, okay? That's magnetic field times area times number of turns. So when you're asked to calculate magnetic moment, it is equal to magnetic field times area times number of turns, okay? So now another way we can write, if torque is mb sine theta, we can write it as m cross b. Of course, m cross b is equal to mb sine theta according to vectors. You know, we learned that in vectors. Okay. Now we see a question here. It says a rectangular coil of length 40 centimeter and width 10 centimeter consists of 10 turns and carries a current of 16 amperes. The coil is suspended such that the normal to the plane of the coil makes an angle of 60 degrees, okay, with the direction of the uniform magnetic field of magnitude 0.6 Tesla. Find the magnitude of the torque experienced by the coil. Now, solution, we've seen that torque is Barney sine theta, okay? So your B here is the magnetic field from the question is 0.60, okay, multiplied by area. Now, we are not given area, but we are given the length and the width, which is 40 times 10. So we can write that as 0.4 multiplied by 0.1. That's length times breadth, okay? Now, N here is the number of turns. In the question, we are given 10 turns. Then I is the current. In the question, the current flowing through it is 16 amperes. Then we have sine theta. The theta is 60 degrees. The angle, it's normal make with the field. So I have a calculator here, 0.6 times 0.4 times 0.1 multiplied by 10 multiplied by 16 sine 60. That is giving us 3.25. So the whole of this now is equal to 3.26 Newton meter. The unit of torque is Newton meter. Okay, so that is it with that question. So let's see another question here. It says a circular current loop of radius 20 centimeter carries a current of 10 amperes. A circular current loop of radius 20 centimeter carries a current of 10 amperes. A. What is the magnitude of its magnetic dipole moment? Okay. B. If the dipole is oriented at 30 degrees to a uniform field of the magnitude, what is the magnitude of the torque it experiences and what is its potential energy? Okay. Now, first of all, we asked for magnetic moment. I told you that magnetic moment is simply current times time. Current times area. Now, we are supposed to have N, which is number of turns, but in this case, we don't have number of turns, so we raise this, okay? So, current times area. The current in the question is 10. The area is a circular loop, so we are not given area, we can find it. Since it's a circular loop, area is going to be pi r squared. So the pi is 3.14 times the r is 20 centimeter, that means 0.2 squared, okay? So I can add here 3.14 times 0.2 squared, okay? So if we calculate that, you have 10 multiplied by 3.14 multiplied by 0.2 squared. So that gives us 1.256, okay? The unit of magnetic moment is amperes meter squared. Current is amperes and area is meter squared, okay? Now, we now have the next thing to look at, which is the next question. It says if the dipole is oriented at 30 degrees to the uniform magnetic field, okay, we are asked to find the magnitude of the torque. So let's see. So what is torque in this case? Sorry, excuse me. What is the torque? The torque, like we have here, is mb sine theta. That means magnetic moment times b, which is magnetic field sine theta. So from the question, we just saw that magnetic moment is 1.256 from A. Then multiplied by B. B is the flux density. The flux density in the question is not given. Okay, it's not given, so we have it as B. We can leave it that way. It's supposed to be given, so, but since it's not given, we have it as B. Then we have sine theta. Sine theta here means sine 30 degrees. Okay, so which if we multiply, we're going to get 1.256 multiplied by sine 30. Okay, that's giving us 0.628. So our answer here will be 0.628 B. 0.628B. Okay, so this is how it works. Now that now leads us to the force between two parallel conductors carrying current. Now remember that when a conductor carrying current generates a magnetic field. Okay. Now if I have another conductor placed by its side carrying current, it also generates magnetic field. Now let me quickly say here that the magnetic field generated by this rod A and the magnetic field generated by B interact with each other, so they will both of them will experience a force, but the force will either be an attractive force or a repulsive force. Now let me say this: if both of them have their current moving in the same direction like we have in the diagram, the force around them will be an attractive force, something like this. It will be an attractive force. It will attract with each other just like this. Okay, but if the currents are flowing in opposite direction, the force they will experience will be a repulsive force. You can check out your textbooks for more explanations on the drawing. So the force experienced by each of them is this, given by mu naught. The mu naught there is permittivity of free space, which has a value of 4 pi times 10 to the power minus 7. That's a constant. Then I1 and I2 are the currents in the wires. L is the length of the wire. Then all over 2 pi r. R is the distance between the two wires. Okay. Sometimes you can be asked to find the force per unit length. Force per unit length means force over length. And the force over length means mu naught I1, I2 all over 2 pi r. Okay, so we see a question here. It says two long parallel wires are 4 centimeters apart. Two long parallel wires are 4 centimeters apart and carries a current of 2 amperes and 6 amperes respectively in the same direction. Remember, when they move in the same direction, the force will be an attractive force. Compute the force between the wires per meter of wire length. Did you see the question? Compute the force between the wires per meter. That means force per unit length. Okay, so which we've seen is mu naught I1, I2 over 2 pi r. Very simple. Your mu naught is 4 pi times 10 to the power minus 7 as a constant permittivity of free space. The current in a wire I1 and I2 is 2 amperes and the other is 6 amperes. Now divided by 2 pi r, that means 2 pi times your r is the distance between the wire, which is 4 centimeters, which you can write as 0.0 0.04 meters. Okay, so I think here pi can cancel pi, 2 we cancel 4 to give us 2, and when we divide, we are going to have 2 times 10 to the power minus 7 times 2 times 6, and in the denominator we have 0.04. That will give us 6 times 10 to the power minus 5. So the force per unit length is 6 times 6 multiplied by 10 to the power minus 5 Newton per meter. Force per unit length, the unit is Newton per meter. So I believe that this is quite clear. Okay, now that leads us to another topic here. It's called Hall's effect. Now the principle of Hall's effect states that when a current carrying conductor is introduced to a perpendicular magnetic field, a voltage can be measured at the right angle to the circular path. Okay, this effect of obtaining a measurable voltage is called Hall's effect. And at that case, let me give you a little explanation here. Now, when you have current, let's say a wire, a flat wire especially, placed in a magnetic field, you have your north pole, you have your south pole, and current is moving in the flat wire. Because of the magnetic field, the current will be attracted, you see, the current will be attracted towards one of the poles, and that attraction, since it keeps accumulating this way, it will create an EMF across the plate. Okay, that EMF created across the plate is what we call Hall's voltage, and we can say there that there is a balance between the magnetic field and the electric field here. Okay, magnetic field is QVB, electric field is QE. If you cancel Q on both sides, you are going to have VB equal to E. So that means V, which is Hall's voltage, is E all over B. That means electric field all over magnetic field. Okay, look at this question here. It says, calculate the velocity of an electron, between an electric field of 30 Newton per coulomb and magnetic field of 20 Tesla. That's here the solution is simply V equal to E over B. So my E is 30 Newton per coulomb, my B is 20, so everything there gives me 1.5 meter per second. I think this is quite, straightforward. It's quite straightforward. Okay, so this is where we come to the end of this particular class. Thank you.